Okay, here is lesson 1B, and this is kind of an additional piece of our introductory lesson on gravitational fields. This is like an addendum to that lesson. And we're talking about the potential energy of gravity in this lesson. So it's a little bit of a different topic, and typically the way that we've always dealt with things in high school physics is that we've looked at forces as part of one unit, and we've looked at energy as part of another unit. Well, really, they're just different sides of the same coin. And so in this unit, we're going to be talking about forces and energy kind of wrapped up together because there's good information and there's useful stuff in both. So let's talk about the potential energy of gravity. In the past, we've talked about EG as being mgh, which is mass times the acceleration due to gravity times a change in height, which is completely fine when we're at the surface of the Earth. But we really haven't considered potential energy of gravity on a larger scale. We haven't considered the potential energy of gravity on different planets or at different distances from planets. And we'd like to be able to do that. So objects at different distances from the Earth, or really from any mass at all, experience different potential energies. And because the force of gravity is very attractive, and is always attractive, it means that if I want to break free from Earth's pull, I need to add energy to myself to get away from Earth's pull. So in this regard, you can think of gravity as kind of an energy well, which means that if you want to get out of this well, you need to add energy to your system. So when an object is in a gravitational well of another mass, you have to add energy into it. And so we've got a little bit of a schematic here. So let's think of the Earth. Here we are on the surface of the Earth, and of course, when we want to blast rockets off from the surface of the Earth, we need to provide them with tons and tons of energy so that they can break free from gravity and get out and get on their way to the moon or wherever the heck they're going. So very often we'll see these energy level diagrams where we'll have an energy well where basically we have this distribution and it shows the differing amounts of energy at different heights. And of course, we would say up here, well, this is where the energy from gravity is 0. And depending on how deep this well is, that would mean how much energy we need to provide to get out of gravity's pull. Okay, so basically, there's a massive amount of energy that's required to break free from Earth's gravitational potential energy. And what we'd like to do is we'd like to figure out what that is. We'd like to have a way of defining that. And as it turns out, when very large distances are involved, we of course, and when different planets are involved, we would use Newton's law of gravitation and some calculus to basically determine an expression for gravitational potential energy when you're not on the surface of the Earth. So this expression right here is true for anywhere. And we get negative g m1 m2 over r. Now here, there is no r squared. So the r squared, you'll notice, has disappeared. And all that we're left with in the denominator is just r. You'll also notice this negative sign. Okay, and this negative sign is the well, it indicates the well-like nature of the gravitational field. That basically you need to put energy in order to break out. Okay, so if you're interested in this little derivation and how we got this, it's well beyond the scope of grade 12 physics in Ontario. But you could check it out in our textbook because it is in there, or you could also check it out online. So let's actually use this in an example. So how much work is done moving a 1,000 kilogram spacecraft from Earth's surface to a height of 200 kilometers above Earth's surface? So we want to take a 1,000 kilogram spacecraft and we want to blast it off. How much energy is this going to take? Well, when we talk about how much energy something's going to take, we're going to look at the difference between these two potential energies. And we're going to do work. So that we have to do work on this spacecraft in order to change its potential energy. So we're going to start with the gravitational potential energy that it has at the end minus the gravitational potential energy that it has at the beginning. And so what we'll do is we'll, of course, substitute our formula in, keeping track very carefully of the negative signs. Okay? You'll notice that, of course, this is Earth, so big M, we're talking about the mass of Earth, and of course, little m, we're talking about the mass of the spacecraft. And when we simplify this, you'll notice we get GMM times 1 over R1 minus 1 over R2. And we can simplify even further and put our numbers in here. Now, of course, this is in meters and this is in kilometers, so we need to do a little bit of unit conversion here before we can actually complete this. But when we do, and we work this out, and we substitute in all of our numbers, we get 1.9, we get a positive number, 1.9 times 10 to the 9th joules, which is a huge amount of energy, an absolutely huge amount of energy. This is the type of question that you'll see in your homework tonight, and you'll be able to try a little bit. So now that we know that, we can do something really interesting. We can talk about escape velocity. We can say, okay, well, if I know how much potential energy needs to be overcome to escape, I can say, hey, how much kinetic energy is required, and then what's the velocity that's required to get out of Earth's gravitational pull? And that's what we call the escape velocity. And it's a really neat little derivation, and so we're going to do that. Basically, we need to provide some rocket with enough energy that it breaks free of Earth's gravitational potential energy. So we're going to take it, we're going to give it a whole bunch of energy so that we can take it from, basically, here it is sitting on Earth, to a spot where we have no more gravitational potential energy left. So basically, we want to be in a spot where I've got 0 gravitational potential energy. Okay, so I don't want any gravitational potential energy from Earth. So I'm going to call that 0. And so here, I want to basically work out, well, what's this velocity got to be? And if I continue to do this little derivation, you'll notice that really the mass of the satellite doesn't matter at all. And I can rearrange, and my escape velocity is 2g times the mass of the Earth, all divided by the radius of the Earth squared, under the square root sign. And that's rocket science, ladies and gentlemen. So here's a little example for you. Find the escape speed of both the Earth and the Moon. So the mass of Earth is 5.98 times 10 to the 24th. The mass of the Moon is 7.35 times 10 to the 22. Here's Earth's radius, and here's the Moon's diameter. So for Earth, I know that escape speed, and now that I have this handy-dandy little formula, I can just use it. I get 2 times g times the mass of the Earth, all divided by the radius of the Earth, and that's under the square root sign. I substitute my values, and I get 1.1 times 10 to the 4th meters per second. The Moon, you try it yourself. Here's the answer, 2.4 times 10 to the 3 meters per second. If you have trouble, we'll take it up tomorrow.